In this section, we are going to talk about revisiting irrational numbers. We'll start with revisiting irrational numbers, then we'll talk about square root of p is irrational, where p is a prime number, and then we'll look into some theorem and examples. Revisiting irrational number. The reason we are calling this as revisiting irrational number because in class 9 we have studied about irrational numbers. What we are doing in class 10 will prove a number is irrational number. So we'll learn about how do we go about proving a number as irrational number. Before we start looking into this, let's look into a theorem which says if p is a prime number and if p divides a square, where a is a positive integer, then p also divides a. Now let's try to prove this. Let's assume a is a positive integer. Now since we know every positive integer can be represented as multiplication of prime factors, and hence we can represent a as p1 into p2 up to pn, where p1 to pn are all primes and not necessarily distinct. Now if we multiply a 2 times, I'm going to get a square as multiplication of p1 p2 up to pn, and again multiplication of p1 p2 up to pn, which will give me p1 square, p2 square, up to pn square. And now, since we are given p divides a square at this place, we can conclude using fundamental theorem of arithmetic that p is one of the prime factors of a square. Next, if I use uniqueness part of fundamental theorem, we realize that only prime factors of a square are p1, p2, up to pn, because the prime factors are these numbers raised to power 2, right? So if I combine fundamental theorem of arithmetic, it says p is one of the prime factors of a square because p divides a, right? P divides a square. And if I look into uniqueness part of the fundamental theorem, I know a square, prime factor of a square are p1, p2 up to pn, and hence we can safely say p is one of the prime number from the factor p1, p2 up to pn. And since a is equal to p1, p2 up to pn, a will be divided by p, and hence p divides a. Now we'll look into another point where we want to prove square root of p is irrational, where p is prime. But before we really go and try to prove this, we'll look into this. We can prove a square root of 2, 3, 5, or in general any square root of p where p is prime. Remember, p is prime. Here 2, 3, 5, they are all prime numbers. And as long as these numbers are prime, square root of them are always irrational number. In other words, you can also remember if there is a number s, it is called irrational if it cannot be written in the form of p by q, where p and q are integers and q is not equal to 0. So in other words, if you have to prove a number as irrational number, try to prove that you cannot represent a given number in the form of p by q. And if you cannot do that, then by default that is irrational number. We'll use these two concepts going forward. So let's take an example of a square root of 2 is irrational. We'll use proof by contradiction method. So what it means, I'm going to assume something and I will prove at the end my assumption is wrong, and hence we can say that square root of 2 is irrational number. Now what could be contradiction of what you're trying to prove? You're trying to prove as a square root of 2 is irrational number, we can assume this is rational, right? So let's assume to the contrary that square root of 2 is rational. Since we know any rational number can be represented as r by s, where s is not equal to 0, so we can find integer r and s such that square root of 2 is equal to r by s. Further, let's assume r and s have a common factor other than 1 and say that is x. I can divide r by x and s by x to get co-prime numbers a and b, right? So in this case, square root of 2 can be represented as r by x divided by s by x, and that, let's say, give me a and b. Then the value of a and b will come in such a way that they will be co-prime. So what do you mean by co-prime? Two integers a and b are said to be co-prime if the only positive integer that divides both of them is 1. Right? So remember, this co-prime is one of the important factors in order to prove square root of 2 is irrational. Now, we can represent the square root of 2 as a by b, and hence square root of 2 multiplied by b is equal to a, and if you square both sides, what you get is 2b square is equal to a square, which then implies 2 divide a square. Now, since we know from the theorem in the previous slide, if p is a prime number and if p divides a square, then p also divides a, where a is positive integers. Hence, since we have proof 2 divide a square, we can say 2 also divides a. So, since 2 divides a, I can represent a as 2 multiplied to c, where c is some integer. Now, if I replace a with 2c in the previous equation 1, what I get is 2b square is equal to 2c whole square, which gives me 4c square, and hence b square is equal to 2c square. What it implies though, 2 also divides b square, and hence 2 divides b. So what we are getting to? We are getting to co-prime numbers a and b, and now we are at a point where we see a and b, although they are co-prime, has at least 2 as a common factor, because 2 is dividing b and 2 is also dividing a. So our assumption that a and b was co-prime is totally wrong now, right? So but this contradicts to the fact that a and b have no common factors other than 1 because they were co-prime. This contradiction is because of our incorrect assumption that square root of 2 is rational, and hence we can conclude square root of 2 is irrational. Similarly, we can prove any number, any prime number, square root is irrational. And now let's take an example of generic prime number. Square root of p is irrational where p is a prime number. We will again use proof by contradiction method. We'll assume a square root of p as rational as opposed to irrational, and we will represent it as a square root of p equal to r by s, and we'll assume there is a common factor other than 1 between r and s, and that, let's assume that is x, and hence square root of p can be represented as r by x divided by s by x. If I assume r by x as a and s by x as b, such that a and b are co-prime, then I can represent the square root of p as a by b. And hence the square root of p multiplied to b is equal to a. If I square both sides, what I get is pb square equal to a square, and let's assume this is my equation 1. What it also implies that p divides a square. And now if I use the theorem of p is a prime number, and if p divide a square, it will divide a as well. P divides a square gives me p divides a. So we can write a as p multiplied to some integer c, and hence if I replace this in equation 1, where a is replaced by p multiplied to c, what I get is pb square is equal to p square c square, which then gives me b square is equal to pc square, which then tells p divides b square. Now and hence p also divides b. Now I am at a point where I am saying a and b both has at least p as a common factor. Why? Because p divides b and p divides a. So p is definitely one common factor which can divide a and b, which is against the fact that a and b were co-prime. And hence we can say, because of this contradiction, square root of p is not a rational number. It is in fact an irrational number. Thanks for watching. You can visit us on www.classisfun.com.